Have you ever wondered about your GPS? You punch in a destination and bam, seconds later it gives you the absolute perfect route, somehow dodging traffic you didn't even know was there. Is it magic? Well, not exactly. It's actually a really brilliant step-by-step method called solving problems by searching. And it's how machines figure out the best way to get from point A to a goal, whether that's across a map or right in the middle of some super complex puzzle.
So how in the world do we teach a machine to do something that feels so intuitive to us? Well, it's all about giving it a simple but, brilliant plan. It's like a recipe it can follow to think through pretty much any problem, one logical step at a time.
Okay, let's make this super concrete. Take a look at this map. Imagine you're in the city of Arad, and you need to get to Bucharest. As a human, your brain just goes to work, right? You see the cities, you start weighing different routes. It's all happening kind of naturally.
But here is the real challenge, the million-dollar question. How do you explain that intuition to a computer? A computer can't just glance at a map and get it. It needs a solid, foolproof system to follow, every single time.
And that system is actually surprisingly simple. We're not talking about some mysterious AI black box here. It's a clean, three-part recipe. First, you formulate the problem. You frame it perfectly so the computer knows all the rules of the game. Second, you search. You let the computer explore every possible path. And third, you execute. Once the best path is found, you go for it. Formulate, search, execute. That is the blueprint for solving almost anything.
So let's dig into that first step, formulation. Before an AI agent can solve anything, we have to define its world. We have to tell it exactly what it needs to know, and just as importantly, what it can ignore.
This slide shows one of the most important ideas in all of computer science. It's called abstraction. The agent, in this case our little robot vacuum, it doesn't see the world the way we do, with all the clutter and chaos. No, it sees a simplified grid, a problem state. It couldn't care less about the color of the rug or what brand of sofa you have. All that matters is, where am I and where's the dirt? We literally filter out all the noise for it.
So, to build that rulebook for the computer, we need exactly 4 things. First up, the initial state. Where does the game begin? For us, that's the city of Arad. Simple. Second, possible actions. What moves can you actually make? From Arad, we can drive to Sibiu, Timisoara, or Zerend. Got it. Third, the goal test. How do you know when you've won? The agent just asks one simple question. Am I in Bucharest? Yes or no. And finally, the path cost. What's the price for each move? This could be kilometers, time, maybe even gas money. You give the computer those 4 things, and the problem is perfectly defined.
All right, so with our rules all set up, now we get to the really fun part, the search. This is where the agent actually gets to work, systematically exploring every single possible path to find a way to the goal.
So the whole journey kicks off from just one single point, the root of our search.
And from that starting point, the computer immediately looks at its list of possible moves and generates the first layer of choices. And then, from each of those cities, it does the same thing all over again, expanding to the next layer of possibilities. And it just keeps going, layer after layer, branching out like crazy, building this huge, sprawling tree of every single route you could possibly imagine. This whole structure we're building, that's what we call a search tree. Just think of each stop, each city, as a node. And each node is like a tiny digital sticky note. It doesn't just say Sibiu. It remembers exactly how it got to Sibiu, which city it came from, the total distance traveled so far, and how many moves it's taken. It's the agent's complete memory of that one specific path. Okay, so the agent can build this absolutely massive tree of possibilities. That's great. But finding a path isn't the same as finding the best path, right? So how do we actually measure success? How do we know if the answer it finds is any good? Think about it. Is the very first route you discover guaranteed to be the shortest one, or the fastest, or the cheapest? Almost never. So we need a way to actually evaluate our search strategy. And we basically judge any search strategy on 4 key things, kind of like a report card. First, completeness. Is it guaranteed to find an answer if one actually exists, or could it get lost and give up? Second, optimality. Does it find the absolute best answer, the one with the lowest cost, or just the first one it stumbles upon? And then you've got the 2 big resource hogs, time complexity. How long are we going to be sitting around waiting for an answer? And space complexity. How much of the computer's memory is this giant search tree going to eat up? And this, right here, is one of the most fundamental trade-offs in all of computing. Searching for the absolute 100% perfect solution might take years, and more memory than a supercomputer even has. So, in the real world, we often have to choose. Do we want the perfect answer next week, or a pretty good answer right now? That's a huge decision engineers have to make every single day.
Now you might be thinking this is all about driving in maps. But the crazy thing is, this simple framework, define, search, execute, is one of the most powerful and widespread ideas in all of technology. Once you see it, you really do start seeing it everywhere.
Take this classic 8 puzzle. The initial state is just the scrambled board. The actions are sliding a tile into the empty space. The goal test is checking if the numbers are in order. And the agent searches through hundreds of thousands of possible moves to find the solution. It is the exact same logic as our road trip, just with tiles instead of towns.
Or what about the 8 queens problem? Here, the initial state is an empty board. The action is adding a queen to a square, and the goal is to get 8 queens on there with none of them attacking each other. The agent searches through the massive space of all possible placements to find a layout that works. It's a chessboard, not a map, but the thinking behind it, identical.
And look, this isn't just for games and puzzles. This framework is the engine quietly running so much of our modern world. It's how data packets find the fastest way across the internet in milliseconds. It's how logistics companies solve the traveling salesman problem to deliver packages efficiently. It's used to design the insanely complex, city-like layouts of computer chips. It's how robots learn to navigate a new room. This is fundamental stuff.
So when you strip it all away, it all comes back to this one really elegant idea. A search algorithm is simply a machine that takes a well-defined problem as its input and returns a perfect, step-by-step plan, an action sequence as its output. So this powerful way of thinking, it's not just locked away inside a computer. We use some version of it every single day, whether we're planning a big project or just figuring out the best order to run our errands. It is a fundamental pattern for intelligent problem solving. So the question I'll leave you with is this. Now that you know the recipe, formulate, search, execute. What complex problem in your world are you going to solve next?